With this, it becomes evident that today's program is poised to be a transformative experience, fostering skill development and enriching the knowledge base of those who embark on this journey. We all have assembled today for the inauguration of the 6-day faculty development program on VLSI chip design and AIML perspective, sponsored by AICTE Training and Learning Academy, that is ATAL Academy, organized by the Department of Electronics and Telecommunication Engineering, BMS ITNM.
I extend a warm welcome to each one of you for this 6 days faculty development program on VLSI chip design and AML perspective, organized by the Department of Electronics and Telecommunication Engineering, which is sponsored by AICTE. So I would like to take this opportunity in the absentia. I would like to invite our respected principal, Dr. Mohan Babu GN, and Vice Principal Dr. Anil GN, and Dean Academics Dr. Satish Kumar for their support and advice. So I take this opportunity to extend a warm welcome to today's chief guest, Dr. Prabhakar Mishra, founder, CEO, Vakini Research Lab.
Welcome you all to this 6 days ATAL FDP program. This FDP on VLSI chip design and AML perspective, we floated to keeping main objective in mind, majorly to bring academicians, research scholars, and industry experts in the field of VLSI design. Because in recent years we have seen an unprecedented advancements in VLSI chip design, leading to billions of transistors on the chip. As we continue further pushing the boundaries of Moore's law, we face plenty of challenges with respect to designing a complex and power efficient VLSI systems. But at present we have emergent technology, AML, which is giving us opportunity to explore more, and it is also giving the opportunity for all VLSI engineers in the field. So with this brief introduction to this FDP, I'd like to brief you on the 6 days FDP schedule with the topics and the speakers for the different sessions they are engaging. So today's keynote speaker is Dr. Prabhakar Mishra sir, who will be addressing you all in next few minutes. So next is trends in micro and nano devices for future high speed and low power electronic systems, and by me, and then state of art and future trends in VLSI industry by Mr. Nikhil Rao, who is an industry expert again for the session, for afternoon session. So then next day 2, we have VLSI for AML, opportunities and challenges by Mr. Vinayak Babu, who is again industry expert running his own business in the field. Next we have data path element design perspective for custom hardware accelerator by Dr. Cyril Prasanna, who is a director R&D in Cambridge Institute. And next we have low power techniques in system on chip design by Dr. Manas Ranjan from SRM University, AP. Day 3 starts with session on issues in physical design and ASIC perspective. Okay, so which will be handled by senior group director in Cadence, Mr. Alok Chandra. Then we have issues in time enclosure and synchronization by Aksar Murli, who is a senior design engineer at Frenes Tech Private Limited, Bangalore. We have design verification system on chip perspective by Sanjay Karambale, senior R&D manager, and Abhishek Saha, a senior R&D manager from Synopsys company. They will be engaging these sessions on the third day. So fourth day we have analog and mixed signal design opportunities in AI, ML, SOC by Dr. Jagdish IT Dharwad. So we have FPGA architecture perspective in reconfigurable computing and system on chip prototyping by Mr. Kalyan Raman, Padmanabhan Kalyan Raman from Intel. So again, memory design in SOC for AML again by Kalyan Raman on the day 4, and day 5th is we have planned industry visit to one of the fab labs. Okay, so one option we have CMTI, but we are trying to explore beyond that because we don't have much opportunity to enter the clean room there. So with that constraint, we are working on Sitara or IISc. Okay, so we are will be able to confirm by tomorrow or day after tomorrow. So it is on 5th day. 6th day we are concluding the 6-day FDP with a topic on network on chip communication perspective by Dr. Prabhakar Mishra again, who is CEO of Wagmin Research Lab. So this is next 6 days program schedule letters with the different topics and the speakers details. I take this opportunity to thank Dr. Prabhakar sir for being with us today, Mr. Nikhil Rao sir for their support, continued support. I take this opportunity to thank our dean and dean student, planning and development, Dr. Ganesh sir, for his continued support. I thank my HOD, Dr. Mallikarjun sir, for motivating me to take up write this proposal, Atal FDP proposal to AICT, and I thank my colleague, Dr. Bhanu Prakash, who has been supportive all these months for starting from submitting the proposal to till date. He has been very supportive in all the regular activities, starting from the planning to execution. And I thank all my department colleagues and all the students, and more importantly participants who have come from different states and all over the state of Karnataka. Thank you all. And I wish you a fruitful FDP. Have a great learning. Enjoy. Thank you.
Good morning to everybody.
Morning, sir.
So it's a very apt topic that BMSIT has chosen for two reasons. One, you can see the codependency between the two fields that have been chosen. There are a lot of algorithms that can be improved in VLSI by machine learning, and a lot of architectures that can be developed for real-time implementation of machine learning or deep learning algorithms on chip. So it's a two-way process. I'm really appreciative of BMSIT for having organized it. They have picked up a set of very good speakers, and hopefully in the sessions that come we can have interactive discussion and exchange of ideas. So with this I conclude my speech over here, but I will continue with the keynote address a few moments later.
Good morning.
Morning, sir.
So I take this opportunity to welcome my fellow colleagues from various institutions to be part of the FDP, which is, as sir was mentioning, very aptly chosen, where I can say the marriage between IT and electronics today happening with VLSI, with the AI and ML perspective, which was long pending from the academician's perspective. Second, my compliments to the Department of ETE, I think, which is conducting a second FDP sponsored by Atal today. I think one they have done a couple of years back on green communication. Today they are fortunate enough to have many industry people to be witnessing this particular second FDP on VLSI, chip design and ALS perspective. And my personal interaction with this particular domain is for the last 5-6 years, where we partnered with the various industries from the recruitment perspective at VLSI, like Path Partner and other industries. And this team of ETE has been very vibrant and active in engaging industry people, especially during autonomous with the various bodies, to have a better curriculum for the student friends here. And I am sure they will be, I think this is the first batch of autonomous sitting here, I believe, right? Yes, and they should be experiencing this type of engagement with industry, what brings to the student community. And I am sure that the students should be part of this 1 week FDP, which is going to be helpful to them because they will be hearing from industry stalwarts. And today, as we speak, the Indian government is pushing this semiconductor design. All these days we're importing these chips from the abroad. Thanks to COVID now, at least we got an opportunity where we can explore this. And close to BMSIT, we have a park which is hardware and chip design park. Hopefully that will be pushing us to even open a new branch of it. Probably the telecommunication department will be taking that initiative to have a engineering program maybe by next year in exclusively in VLSI design. So with this, I congratulate team ETE and compliment all the faculty colleagues from various departments, from various colleges, and my student friends who I wish to be part of this FDP and utilize the learnings from this and ensure that we have a better future. Thank you.
Keynote address from Dr. Prabhakar Mishra. First session, I would like to address to the gathering, give a brief biography of Dr. Prabhakar Mishra. He holds a PhD in autonomous system. His research has carried out in Indian Space Research Organization for autonomous navigation of rover for space applications. He is a senior member of IEEE and member of IEEE Robotics and Automation Society. He holds a bachelor degree from Karnataka University, Dharwad, and master degree from NITK Suratkar. As an avid researcher in the field of computational efficient algorithms for AI and ML, with emphasis on hardware architectures for their real-time implementation, he has published 6 journal papers and more than 50 conference papers spanning over 20 years. His area of research include algorithm for autonomous systems, system-on-chip architecture for AI/ML, reconfigurable computing using FPGA and edge computing.
So this field is a trade-off. If you are looking at optimizing everything, then that's not going to happen. So you have to pick and choose what is good for your particular application. Why am I saying this? Because I think as far as most of the practitioners would be concerned, if you are practicing this field, you must be aware that VLSI comes with a lot of constraints per se. It comes with constraints of area, that is, you can't have die size as much as you want. So the area or the real estate is limited. Within that limitation, you cannot dissipate as much power as you want. And the problem is, the faster you want to go, the more power you have to go. So if you want speed, power dissipation goes up. Power dissipation goes up, its cooling arrangement, its cost, its economics gets hit. To avoid that, if you say I'll increase the chip area, then the die size limitation kicks in. So you can see this cat and mouse game being played out between software and hardware right from the beginning. Right from the beginning. You remember the good old transistor days? You had DTL logic, RTL logic, TTL logic before you came to CMOS. And you had small scale integration, then medium scale integration, then large scale integration, then very large scale integration. So if you look at it in an evolutionary way, how things have evolved, for instance. one key aspect that you can recognize is the initial insistence on programmability. Does that ring a bell? Right from the beginning, people have tried automation, even in normal electronic circuit design. Now, one thing that we must remember when we are speaking about, AI ML perspective per se, is something which I have found many people do not appreciate. I am not saying that they do not know per se, but they don't appreciate that fact. Any AI ML algorithm that you want to build, it assumes a prior procedural knowledge. Are you understanding that sentence? AIML is not a fix-it-all solution. If you want to automate something, you must have the procedural knowledge on the basis of which you will write a software which will help in automation. You can't say that an AI algorithm or an ML algorithm will get that procedural knowledge for you. I don't know whether you are appreciating that. Most of us think AI, ML, write a software, but to write that software, you should have procedural knowledge. So then you can say, then what is intelligent about this whole thing? The intelligence kicks in, or seemingly the intelligence kicks in, when you have procedural knowledge with one set of parameters, and you have procedural knowledge with another set of parameters, but you don't have the procedural knowledge between them. Then you can use any kind of statistical inference engine. Any kind of what is AIML after all, if you look at it mathematically? You are trying to make statistical inference, statistical guess on what could be the best fit given these two. But if this is also not given and this is also not given, then how do you approximate? Any statistical algorithm will not work. So that is one key part that you must remember. So if you look at programmability, you have a scenario where you have functions that are fixed. I hope I am speaking predominantly to circuit branch participants. Right. So, for instance, you have an AND gate, you have AND gate, or you have an OR gate, you have logic gates on chip. You are not changing the functionality when you are designing using a PLD or a PLA. Correct? The functionality is not changing. You are only changing what input gets connected to which of these functionalities. Right? So we started with hardware programmability in that sense. So you have a certain number of inputs, then you have a certain number of gates. So initially they started with wide input AND gates followed by narrow input OR gates, or wide input OR gates followed by narrow input AND gates. Of course with some inverters, because you can't have all straight functions. And then you are trying to find a method to map these inputs, route them to the gates and get the output. This was the concept of programmability. If you are having any questions, you can interrupt and we can discuss. I am not saying I know the answers to all of it. So to discuss, I can also get some thought processes going. Then came this whole gamut of computation. The essence of development of electronics was how do we compute? So how do we compute? How do we perform arithmetic functions? So you came up with the idea of a ALU, a set of registers, and some piece of code residing in an external memory, and something that is scheduling all the operations on this. Correct? Isn't it? Now within this gamut, I would like you to ponder. Sometimes it is very good idea to take a seat at. When did we or why did we move from integer arithmetic to floating? Is floating point arithmetic really that necessary even today for all applications? If you are saying, or if you are looking at physical experiments or instrumentation or making sense of data in the nanoscale, picoscale, etc., there it is required. But for all applications that we use, I don't think we require that precision. Is that point getting clarified? Not making sense. Right. So, what this brings us to is, if there are constraints of area, if there are constraints of speed, if there are constraints of power dissipation, is there a way we can change data representation for inferring something without getting into too much of precision? You will find Google has gone exactly the same way when they have developed the TensorFlow processor, tensor processing unit. The area is the same. What they have done is they have taken 8-bit integer arithmetic. They have developed a small multiply and add, which we call as MAC unit, 8-bit integer MAC unit. But what they have done is they have an array of 8K cross 8K, 64,000 such units as an array. So they are parallelizing the computation and they are able to get a lot of throughput. But get a lot of throughput at the cost of resolution. That's why I used that couplet before. Sher sunaya tha. Because for that, you can't get both. So you let go of precision, make more parallel computations on chip possible. You hold on to precision, then the number of computations will come down. It's a trade-off again. There is another paradigm within this. What has happened unfortunately over the last 20-30 years of VLSI development is advances in analog VLSI has not kept the same pace with advances in digital VLSI. So we speak about neural networks, for example. Most of the people will be using some form of a neural network. So the problem there is, if you look at any activation function in a neural network, it has an analog characteristic. What do you do when you use a digital computer to solve this problem? What we have been taught in our classrooms, piecewise linear approximation. Correct. Most of us do not still understand, or I will not use the word understand. We don't completely comprehend that we do not have a closed form mathematical solution for a non-linear equation, a set of non-linear equations. So we want to hide that inability, not to expose ourselves. Piecewise linear approximation. Correct. What is its approximation in digital electronics? How do I approximate that in digital electronics? If I want to use a digital computer, I make use of a lookup table. You understand? So I have, say, 3 or 4. Suppose I have 3 piecewise linear regions. For every region, I have a lookup table which maps, if this is the input, what should be the corresponding output. But the more complex the function becomes, the larger your lookup table size becomes. Correct? So how do you beat this problem? We could have beaten this problem if we were able to design analog circuits that could give us that function. But that unfortunately has not kept pace thus far. So I'll just begin with a few slides, right, highlighting some of these aspects, and probably we can pick up from there. I also invite some comments and your thoughts on this. So that will really help me immensely. Yeah. So if you look at the evolution of computing devices, alright, you will see you started out with vacuum tubes, then you started out with discrete transistors, alright, then the appearance of MOSFETs, then what you are seeing today, a complete multi-core system, multi-processor system on chip. And in the evolution of all of this, alright, one thing that is really important is this whole business of programmability, as I was discussing. You have the same set of hardware, the same piece of hardware, you are running different applications on the same hardware. This is a little different from configurability. The meaning of configurability is you are trying to make the same hardware behave differently at different points of time, which is the flexibility you get when you use an FPGA. Correct? Most of the FPGAs that are available in the market, they come with some form of configurability so that the same lookup table or the same RAM, set of RAM cells can be made to behave differently. At some point of time you want it to function as a AND gate, you can do it. OR gate, you can do it. Exclusive OR gate, you can do it. So this gives rise to configurability. And if you want to save space, you go one step ahead and you say, now I am going to introduce reconfigurability. Not just configurability, reconfigurability. There's a little bit of application trade-off in this. For instance, when we design SoCs for space applications, the problem there is radiation resistance. So you can't have something which can be corrupted because of UV radiations coming onto that. So therefore you don't want reconfigurability, you just want one-time configurability. You compare and contrast that with the commercially available FPGAs that are available in the market today. So they are SRAM based and they support reconfigurability. You can keep changing the same lookup table, will keep behaving differently at different points of time based upon what is the configuration bits that you are using. So that's the difference between programmability, configurability and reconfigurability. Right? So if you look at generations of the processors, you can clearly see the movement from MSI to LSI to VLSI, right, to a proper system on chip design that you are seeing today. So of course this is something which is quite self-evident. Now, if you look at this slide, really gives you a much better perspective on this. Right? Probably this will give you a better perspective. You look at the advances in processor, alright, the performance of the processor with respect to time, and the performance of memory with respect to time. So you can see how that gap has gone on increasing as the generations of processors have gone. What does it tell you? It tells you today, when you are making computations in hardware, you are not limited by the processing unit. CPU is not the bottleneck. The bottleneck is memory. In fact, it has gone one step ahead. Even if the bottleneck is memory, that bottleneck is because of transferring data from memory to the CPU. Because the wires are not speeding up in the same scale. Are you understanding that? The problem is not with functional units. I can give you as many functional units that you want on chip. But how do you put data to them and get the results computed? That requires a bus. requires a set of bus for wires for the data to travel. As you are shrinking the feature size, that wire is now behaving like an antenna. So all the transmission line effects are getting predominant, and because of that, this performance bottleneck is coming.
So what interest if memory and the computing on the same chip?
Even if you put it on the same chip, unless you are doing in-memory computation, that's a different paradigm. Even on chip, if I have a processing element and an adjacent memory device, still this transfer is happening through a howsoever small bus it may be, but still it's happening through that. Okay? So this is a crude example that I give to most of my students. I generally, get some of our students, I ask them if there's an internet service provider who gives you an internet connection through a USB, through a coaxial cable, or through fiber optic, which one will you prefer? And invariably all of them will tell fiber optic cable. Then I ask them that fiber optic cable, where are you terminating on your laptop or on your CPU? From there it is just copper that is going. So if the copper cannot take the data rate that you are throwing with the fiber optic cable, then what is the meaning of putting the fiber optic cable? The transmission is not band limited by the fiber optic cable. The data rate is band limited by copper. But marketing is different, reality is different. You would still prefer a fiber optic cable with a much higher data rate than what you are. So either our understanding of the bandwidth and data rate supported by copper is not correct. Either that must be true, or the other side must be false. Both of the things cannot become true at the same time. So right now actually you are in a paradigm in VLSI where everything is band limited by communication. Things are not band limited by processing elements. I still don't agree things are so band limited by memory either. It is the transfer between the memory and the processing element back and forth. So of course people are trying, to answer your question, people are trying their hands at in-memory computation. If you are able to do that, then this bottleneck can be minimized. I'm not saying avoided, it can be minimized. So this is one good slide to ponder. Then people have designed a lot of, if you look at the developments, people have tried a lot to reduce the latency of data transfer between memory and the processing elements. And I don't want to get into all their methods. Most of this you would have learned also. Multiple level of caching, isn't it? And having local memory, then distributed memory, memory within processing elements. Right? But all of them again suffer from the same effects where in submicron technology you are having this whole problem of memory, the wires not scaling as they should. This also I think is something worth noting. Right? So as we are progressing now, we are catching up with the diminishing return on investment for silicon. This is a very serious issue facing the VLSI industry today. So what it simply means is microprocessor effective work per clock cycle, that is instruction per clock, goes up by the square root of number of transistors. You put more transistors, the performance will go up. There is no doubt about it. Alright? And the clock rate also you can increase as the feature size reduces. But if you scale it by a factor of 4 instructions per clock, the microprocessor performance doesn't scale by the same factor. Alright? So why does that happen? For the reasons which I was talking about is put there. Wires do not scale in the same way as technology. And there are other bottlenecks. Once you increase the data rate and the wire sizes become small, crosstalk, inter-symbol interference, signal integrity, all those problems become more dominant. So now you are having a VLSI firm where you took people who knew digital logic design. Now you are having to take communication systems expert to solve this problem. Right now the bottleneck with VLSI industry is not architecture. You have a sea of people who are very good in digital architecture. Very, very good. But the problem, the main constraint is coming from wires. So you require the same analysis that we do in communication system design. The same analysis has to be done for on-chip communication. I am not speaking about off-chip communication. Just to give you that perspective which you are asking. For on-chip communication. Alright. So this is a bottleneck. Now this is another interesting slide that I found, and I am telling you upfront, none of these slides are mine. Alright, I have taken them from various sources and I have quoted the references from where I have taken. So all of us continue to harp on Moore's law, and in my own practical experience, Moore's law is the most abused law in VLSI. In 2004, everybody said Moore is dead. You remember? Then they said no, he's still alive. Then in 2017 they said now he is finished. Yet he continues to live. But there is this slide shows you a very different perspective. It's like the same thing. The world as it appears to us because of our sensory system is not the same as it appears to an ant because of its sensory system. Correct? This actually reminds me of a discourse that my guru was having with me many years back when he said, Adi Shankara said, Brahma Satyam Jagan Mithya. And I said, what is the meaning of that? So he said, alright, you are there, a dog is there, a cat is there, an ant is there, a bird is there. All of you are perceiving the same world. Is it looking the same to everybody? No. Which among them is true there? So this is just a change in perspective. I understand. So one is, you take and design complex superscalar processors, put that on a die and think that it is performing really well, versus you reduce the kind of instructions that it performs. So your data path shrinks. Because your data path shrinks, you have more space. Now you can have multiple such data paths and push up the performance. So that's what he's saying. A scaled 32-bit 5-stage RISC occupies just 1,000 of the current compute die size in silicon. So now, this begs a question. Instead of having logic gates on a chip, that each logic gate, should it not be a 32-bit RISC processor? It is possible. No. You can have thousands of these fellows on chip. I am telling you, the bottleneck is not processing element. You can have a lot of 32-bit RISC processors in an array. The problem is coming in interconnecting them on chip. Its speed performance is not scaling like how the processing elements are increasing. You are able to increase processing elements. So that just shows you a very good illustration of why not to stick to Moore's law, why not try to beat Moore's law, but find intelligent alternatives where you are still able to push the throughput. And this 32-bit 5-stage RISC, you imagine if you can push that to 8-bit integer arithmetic, how much the die size will increase? I'm sorry, how much more die size will be able to use? So that's exactly what the Google TPU fellows have done. They have not done any magic. They have let go of resolution. They have caught hold of 8-bit integer arithmetic saku. Even in 8-bit integer arithmetic, namage division bada. So it's saying something like this. I will illustrate this with an example so that you will be able to appreciate it better. See, let us say my objective is to determine whether somebody is sitting on this chair or not. Occupied or not. Alright. Do I need 10 to the power of 32, 10 to the power of minus 32 kind of a precision to say that this chair is not occupied? It can be done in binary. If I have a proper sensing mechanism, it's a binary answer. then why do I need that 128-bit double precision floating point format? For what? If I am doing scattering experiment in spectroscopy, I understand, fair enough, there 10 to the power of minus 26, minus 27, because looking at subatomic particles. But to answer this question, that precision is not needed. And if I want to say the confidence I want to increase, I sense and then I say, alright, I want to increase the confidence of occupied or reduce the confidence of occupied. Why should I divide? Why should I not shift? The confidence of occupancy is 1. Another sensor says somebody is sitting on this chair, I will make it 2. 2 to the power of 1. One more sensor is saying it is occupied, I will make it 2 to the power of 2. Always operate in powers of 2. If I operate in powers of 2, my job is done by shift. I need not even multiply, I need not even divide. Multiplication again is not the headache for me. The main headache is division. If you look at a class of AI and ML applications that you are using today, in any field, you will come across at least 95 to 96% of applications that do not require double precision floating point resolution. You are not handling those kind of problems. Even if you say autonomous driving, because I am working on it, what do you want to say? The road is occupied or empty. You want to say to the nanometer, ye nanometer occupied hai ki nahi. That way if you are making decisions, your vehicle itself is in feet. And if you are asking next nanometer whether it is occupied or not, does not make sense. So if you can come across a class of applications where you can trade off on resolution, then you can have a lot of benefit in terms of performance boost. Right? So that I thought was an interesting perspective to give. Right? So now, this is a view that is catching up in industry. Instead of system on chip, we start talking about cluster on chip. What does it mean? Use multiple processors, right, on a single chip. So performance will go up linearly as you scale the number of processors. Of course, it will require proper, algorithmic scheduling. That is there. That goes without saying. Proper scheduling must be there. All right. Then, since these processors can be pre-verified and put as an IP block, right? So, scaling as many instances of that is easy. One processor you have completely characterized in terms of its area, performance, power dissipation, delay, everything. Later, it is just about putting them together and having a proper communication bus across them. Right? So, what the key takeaway is, now one must not talk about MOSFETs anymore. What is the new MOSFET that we have in VLSI industry today? 32-bit RISC processor. That is a MOSFET. That doesn't mean that it will not teach MOSFET in classes. That's not what I am suggesting. But what I am saying is, if you want to get into digital VLSI design for AI/ML, your MOSFET or your single switch is a 32-bit RISC processor. That 32-bit also, I am not sure why people are still sticking with it. My own gut feeling based on my design experiences, an 8-bit RISC which just does multiply accumulate is more than enough for a series of problems. Some problems I do agree where division is critical. Right. So there probably we can still do with a fixed point divider. I am still not convinced for a majority of applications we really require a floating point arithmetic unit which does division. Because I am not aware how many of you have tried your hands at it. It is the most difficult thing to design on chip, a divider. A multiplier is really easy because the simplest what you can do is shift and correct. But you can't do that for a floating point division. So it takes a lot of space. So this is the key takeaway. 30 years ago, Intel 4004 used 2300 transistors. That is how you started with, right, your processor. When will we use 2300 32-bit RISC processors on a single chip? That is the question. Just to give you a good perspective. Alright. So these are the key takeaways up to now. You have a great 30-year history. Alright. The challenge is for the next 30. Alright. All of us are seeing that in the generational gap that we have. Our fathers, they struggled. Correct. We saw their struggle. Correct. But our next generation, they haven't seen that struggle. I don't know whether you have felt that. So the challenge for us is the next generation, not what had happened before. So this 30 years of history is washed off. The next challenge is for the next 30 years. Right? So it's not that, there's a wall in speed, in power dissipation, in performance. But the rate at which performance is going up, that is diminishing. It's not that from one node to the other node, performance is not improving. But it is not improving at the same rate. That is the problem. Right? So that's what is the meaning of saying diminishing returns on silicon investment. Then the thing is you need to make use of the right metrics. The whole insistence of, as I was telling precision, resolution, data rate, how much of computation is necessary, should I keep on computing? It's like this again, the same chair example. After 5 sampling of this, if the chair is saying, if it is saying, my inference is saying it is empty, should I continue to keep sampling? Just because I have a sensor, alright, and the sensor is supporting data sampling and acquisition, I have come to some reasonable conclusion that this is empty, but should I keep on sampling? If I keep on sampling, then I have to keep on updating in the computational unit. Is that necessary? Where do you stop? These are the new paradigms that you have to address. Right? So what is the new direction? Consider multiprocessing. Put multiprocessors on a single piece of silicon be much easier to use efficiently than today's multiprocessors. So those who are really the key, right? You need to look at performance per transistor and more critically performance per watt. As far as the industry goes, those are the 2 critical decision making points actually, if you are trying to. And this, whatever I have spoken thus, I have taken from John Anderson's lectures.